Thank you very much for introduction, and also thank you very much for invitation. So Vienna is like my second home. I mean, I study here. First home. Actually, one of my mentor professor is also here. It is really nice, actually. So anyway, the talk is about non-monotone forward-backward splitting method for a class of finite, infinite-dimensional, non-smooth, non-convex problems. So it is actually in the spirit of the two previous talks, so which means that I am also coming from this PD constraint optimization community and also wants to try to implement and also, let's say, efficient algorithm for these kind of problems. So first of all, I will introduce and also my problem and give some motivation, which kind of problem we want to solve. And then I will give an overview of the algorithm and I'll show you some of our theoretical findings concerning convergence and also complexity results. And then I show you some numerical experiment that actually validate our theoretical finding. And at the end, I am going to next problem, which is actually our result does not work, but we can also adapt our proof somehow in a different way. Okay. So looks a bit technical, but this is actually the problem that we consider. This is actually the composite problem, as we know, and also this is defined in Hilbert space with the scalar product and also norm, and this is infinite dimensional problem. So we have this condition that R, function R, is actually proper, convex, and lower semicontinuous, and it is assumed that it prox is easy to compute or explicitly computable. And the first function f, capital F, is a Fréchet differentiable function, its domain. And also we assume that the gradient of this function is globally Lipschitz continuous. So we have another condition, which is actually, it is important in the case that we have non-convex case, that we also assume that the gradient is weak to strong sequentially continuous. So coming back to these conditions, first of all, if we are in the finite dimensional case, we can see easily that A5 follows from A3. So because all of the norms are equivalent in the case of finite dimensional spaces, and if F is weakly lower semi-continuous and coercive, then we can also relax A4 in the case that actually we have Lipschitz continuity on any weakly compact set. And the last one is only we need it if we have a non-convex scenario. So in the case of convex scenario, we don't need actually the. So one of the problems that we consider is actually this problem. So I'm coming from model predictive control, and we are working. We need to solve many of these kind of problems. So which means that this is actually a kind of PD constraint optimization. We track actually 0 here with respect to some norm. And this is nonlinear PDs. We have nonlinear term. It is a parabolic equation. And the control of the variables that we want to find is that enter in the right-hand side of the equation. And this is, you can imagine that this is our domain, and we put like a 13 indicator functions, as you can see here, one of omega 1, and this, sorry, it should be R. But anyway, this is actually the support of this indicator function. And the variables that we want to find is this variables UI. So this is our, let's say, optimization variable. And here we have L1 norm for our control vector. So which means that we don't want to actually, we want to have a sparsity in the vector of the control. So you can consider the case that we have a room, and this is the heat equation, and we want to actually control steer or the temperature of the room to some constant, so some in this case is 0. And we have these heaters, like 13 heaters, but you don't use all of them because they're expensive, because of the gas or whatever, and you want to use actually only a finite number of them. So you need actually kind of sparsity here. First of all, this problem can be written as the composite function that I introduced before. So you can consider the optimization space as a L2 function. And also you can again consider the control to state mapping or solution operator as the previous talks. And then you can write your problem as the following, let's say, problem with this F and R, which is actually, in this case, R is actually L1 regularization norm, which is convex, non-smooth. In this case, it's actually smooth. So to give you some feeling and and also about the simulation. You can see that in this case here, so it does not work. Yeah, you can see that this is the temperature, and these are the control, and you can see that we want to steer our, let's say, the temperature to 0, but we don't want to use all of this heater here, and you can see some of them are turning on and turning off through the time. But nevertheless, you can see that they are working. So that's also one of the applications that we have. So the problem is non-convex because the PD is actually nonlinear. And yes, and we have also this convex regularization term which promote the sparsity. So here you can also see the evolution of the, let's say, the absolute value of this control. You can see that some of the control, they have not been used because of this sparsity, and some of them use only in some short interval at the beginning. So now I'm going to the algorithm that I use to solve this problem. So the algorithm is actually so well-known forward-backward splitting algorithm that you have the prox operator for the, let's say, convex part, and you have also some gradient. You go in one gradient direction for the, in the direction of the smooth part. So it is a well-known algorithm, and I just actually known some of the literature here, but there are many. So if I forget you, please forgive me. So anyway, the idea is here to find these actually step sizes and also generate a sequence of the iterations that converge to the stationary point of this problem, which is defined as follows. 0 is the subdifferential of the r plus the gradient of the, let's say, smooth part. It comes. I didn't say how. But anyway, the algorithm that we want to use is actually a combination of a non-monotone line search and spectral gradient step sizes. So yes, first of all, we use actually forward-backward splitting argument, as I said before. What we do here, we just define this gradient mapping, which I think some people also call it also forward-backward envelope. And in this case, you can formulate this proximal forward-backward gradient method as follows, which you can see that there is some similarity or analogy between the forward-backward method and also classical gradient method. And also, you can prove that U is actually stationary point of our problem if this gradient mapping is equal to 0 for every positive alpha. So as I said before, I wanted to use this Barzilai-Bovine step size spectral gradient method because I have a really good experience in terms of the PD constraint optimization. And you can see that the original step sizes look like this, that you try with these step sizes to approximate the curvature of the Hessian matrix, but you know that they are cheap and also they accelerate the computations. Convergence. But as we know, you can prove the convergence for these step sizes only for the case that the problem is actually strictly quadratic, even in the smooth case. So therefore, we need some kind of, let's say, safeguard. So we also introduce another step sizes, but what we do is that we also replace this gradient for the, let's say, smooth part with this gradient mapping operator. So in this case, we want also to capture some of the information of the from also the non-smooth part. So anyway, this is the line search that we use. This is non-monotone line search, and I think first time I have seen the paper of Wright and Novak that they also use it for the Lasso problem. This is kind of similar, but different. We have here the gradient mapping actually. So what we do here, this is kind of sufficient decrease condition or Armio rules, but we have what we have here. We don't actually compare the function value in the next iteration with the previous one, but with the maximum of the function value with the previous one. And we also start as an initial trial for our line search as one of these BB step size. And then we use actually backtracking argument in order somehow that this condition is satisfied. Okay. So, okay, now the question is what we can prove for this kind of line search strategy. First of all, we can prove the equivalence of the line search method or algorithm, even for the case that we have no Lipschitz continuity for the gradient of the smooth part. So you can prove by contradiction and using some continuity argument for the gradient mapping that after a finite number of iterations, the line search will terminate. Also all of this again. And under Lipschitz continuity, we can prove that the gradient mapping of the iterations converge to 0 actually with this 1 over square root of k. And normally for proving this result, first of all, you show that there exists a monotone decreasing subsequence of its iterations, and then we use also the fact that we can, let's say, bound the gradient mapping at any next iteration from above for the previous iteration with some constant which is independent of k, and then we can prove that the whole of these actually sequences converge to 0. And also, we can also drive the worst case evaluation complexity for finding the epsilon stationary point, which is also kind of important because every gradient mapping in our case means that solving one nonlinear PD and also one linear PD. And every function evaluation is actually solving one nonlinear PD. And then we can also show that every weak sequential accumulation point of iterations also is a stationary point or problem. So what we use here is the fact that the gradient is actually weak to strong sequentially continuous, and the subdifferential of the convex non-smooth part is demi-closed in both of the topology. I mean talking about the product topology of the weak and strong. Okay, for the case of convex case, we have a better, let's say, convergence rate. We can prove that the function values also, the sequence of the function values converge actually to the optimal one with a rate of 1 over k. And also we can prove that the sequence weakly converge to a minimizer, and also the shadow sequence converge strongly. And here we are actually in the scenario of the quasi-Fréchet monotonicity. So we need, first of all, we show that our sequence are quasi-Fréchet. So additionally, under quadratic types condition, we can prove the R-linear convergence for our function value iterations, and also we can also prove that even we have a strong convergence for our sequence. So I just, for our numerical validation, I just consider this PDE. This is again nonlinear elliptic equation, and we have this sparsity-promoting L1 norm, and also constraint for a control or control constraint. And again, we can consider as a space for a control or an optimization variable, we consider the L2, which is a Hilbert space. And again, by defining solution operator, we can write our problem as a, let's say, again in the composite form, where f, the smooth part, is defined as follow with this actually solution operator or control to state mapping, and also the convex non-smooth part is defined as follow, where this is the L1 norm, and this is actually the indicator function, which is corresponding to this convex. So, and also with standard computation, we can prove that the gradient of this smooth part is equal to the P, where P is actually the solution of this weak solution to this problem, which is actually a linear problem that we call it also adjoint problem. And for this problem, you can verify all of the conditions that I have from A1 to A5. And about A5, normally you can prove that this guy lives in the more regular space. In this case, is actually H10, and then you can prove that this actually compactly embedded in actually less regular spaces like L2. Therefore, you have this actually weak to strong continuity of the gradient mapping. So now I'm showing some numerical experiments. Here we have different direction of our algorithm. And this is the number of gradient evaluation, this is the number of the function evaluation, and this is also for the time. You can see that in this case, we have a fixed step size, constant step size. Here we have a Behzad-Azmi, the first one of the Behzad-Azmi, let's say the original one, and ABB is kind of alternating between two steps. And here we have this new one, BB1, that we actually introduced with the help of this gradient mapping. And this is actually alternating between these two new ones. And we have also, let's say, used non-monotone line search for the worst case, as you can see here, and also monotone line search also for this worst case. So what we can see is that the worst performance is actually for the case that we have a constant step size. We have so many here, a lot of gradient-like evaluation. You can see the less number of gradient evaluation is obtained by this alternative BB, the new one. And you can also see that the performance of the non-monotone line search is far better than the monotone line search. And you can also see here also in these figures. What we have also realized is that having the same, let's say, line search is kind of important. For example, with some initial condition, we have seen that, for example, BB1 does not converge. So you need kind of safeguard, otherwise it does not converge. How much time do you have? Okay, this is so far so good. I'm going to the next problem, which is actually switching control. Well, we have here different scenario in the sense that, okay, we have again this parabolic equation, as you can see, and also we are tracking against 0 with respect to this norm, and again our optimization variable is actually this vector, which has these components, and this is the control we have, which is actually a linear combination of the Dirac's function, which means that we put some Diracs in our domain, and we try to actually control the amplitude of these Diracs. And we have here some kind of cardinality constraint, which impose switching. This cardinality constraint tells us only one of these Diracs are allowed to be active. So we have switching, so which means that imagine you have also a domain or something, you want to influence the temperature with lasers, but you are not allowed to put laser everywhere, but you can just point in some point. I mean, at time only in one point, and switch between several points. So here, this L0, as we know, is neither convex nor continuous. So therefore, this set is not weakly sequentially compact. So even the well-posedness of this problem is not clear. So, and the idea is to steer the energy of the system to 0 with a switching Dirac actuator. And again, first of all, it is not clear how the stationary point for these problems are look like. So what we can do is that we can write the Pontryagin minimal principle for that problem, and then we have the state equation, and then we have co-state equation, and we have this gradient condition that is here. So for almost every t in this interval, we have this condition that beta, which was in the control cost of uj, the j component of the stationary point, plus the co-state evaluated at xj should be equal to 0 for all of the components which are non-zero. So this is kind of combination of M stationary with Pontryagin minimal principle. And again, we can use this, the previous idea, so we can transform this problem to our, let's say, composite problem. So what we can do, again, we can introduce our control to state mapping, as usual, which is smooth part, and then also we can define the non-smooth part as an indicator function to this set, UAD. But UAD was the set that we had before, and as we know, this set was non-convex, and therefore we have some problem. This cardinality constraint, first of all, the projection is not unique, and also we have non-convexity. So therefore, the proximal gradient method in this case looks like this, and UK plus 1 is a projection to this set of UK minus 1 over alpha k, gradient of the smooth spot. Again, we can write it as before, but as I said, this gradient mapping is now the set value, so it is not single value. So here we cannot use the line search that we have beforehand. So because the the smooth part is not convex, and also this project, and also not Lipschitz continuous, so we cannot control, let's say we cannot prove the Lipschitz continuity for the gradient mapping. So we need also have control on whole of the sequence. So therefore, it is important in our line search to consider the convex combination of the previous, the maximum of the previous m iterations and also the previous iteration with some delta, which is actually strictly between 0 and 1, but it's not equal to 1. Then we can, let's say, have a control on the whole of the sequence of the iteration. So what we can do here, you can prove that, again, that our algorithm is well posed, so which means after finite iteration, it also terminates, and we can also prove that these sequences also converge with a rate of 1 over square root of k, and we can prove that every weak sequential accumulation point of sequence is also Pontryagin point. So here we have also, I show you some examples how the things work. So what we do, we put like a 4 places as a Diracs. This is actually the placement of the Dirac. So, and yes, and we want to switch between these 2 points, our boundary. So if I show you the simulations, you can see that, first of all, we can, let's say, send the energy to 0, and we can switch between these 4 actuators. And only one of them through the time is active. That's exactly what we wanted to. So, and with that, I would thank you for your attention.